All right, Kubernetes infrastructure of the future. I guess my button won't work. That's too bad. Maybe it might not be actually. Oh, there we go. Okay, who am I? I'm an infrastructure developer, so I work for Sciax for a games company. My job primarily when I was hired is to go in, take all of their old, disgusting code, and make it new, make it pretty, make it scale. During the pandemic, we saw an unprecedented amount of users. So we have a ton of players. We almost tripled our average player base, which made all of the stuff that we developed just crash and burn. So continuously our player graph was going up and diving, and then we fix it, and it'll go up again, and it was diving. So that was my job. Before that, I had a lot of practice with Kubernetes, but I didn't necessarily have a ton of practical experience. So this was one of my first jobs, and it gave me the ability to kind of learn it as someone who was new to the field. What are we going to cover? We'll cover containers, why containers are important, and why all your apps should be in containers no matter what. They're the best thing. Second, we're going to cover what is Kubernetes, how does it work, why Kubernetes, and thirdly, we're going to talk about some problems and some use cases as to where Kubernetes can come in and solve your actual issues as a developer. So what did a games company use Kubernetes for? Firstly, we had over 300 dedicated servers in 3 different continents, in 6 different data centers. That is a lot of servers to manage. So in total, I think, yeah, it went up to 1.92 terabytes of RAM and over 2,000 CPU cores. That's a lot of RAM, that's a lot of CPU, and that's just a lot of resources to evenly use without losing a ton of money. We would need to create game servers on demand. We needed to track game server location. We also needed to improve developer experience, and we needed to automatically recover from failure. These servers, we would have about 1 every single week. It would die out. There would be a disk failure. Maybe some technician tripped over the cable in the data center. It happened. It was really difficult. Sorry, it was really difficult to work with. So first, we're going to cover containers and why you should use them for your apps. It's difficult to understand Kubernetes without containers. So this is one of those core building blocks that's really necessary to know about. So traditionally, you have different app deployment models. You have virtual machines. How many of you know what a virtual machine is? Anyone? You use virtual machines? Okay, I'll give you the brief concept. So you have bare metal servers. That's, you have a physical machine. It's got Windows on it. You put your app on the Windows machine. Easy peasy. You have virtual machines, which is one additional layer. So instead of having Windows on your server, you install something like VMware or some operating system, and that allows you to have a bunch of little computers inside of your computer. It's pretty much the most popular way nowadays of having servers, because that way, if you buy one massive server, which is a lot cheaper than 6 little servers, you're able to have all of your apps distributed across them, and they're in their own little tiny container. So deploying on bare metal, the good about it, it's high performance. It's easy to understand. You have one box, you have one app on the box. The bad, you have no isolation. If you have some super secure application and you install some other vendor random software that you need for accounting, and the accounting software gets hacked, so does your important software that you've written that's secure. You have no out-of-the-box fault tolerance. If that server lights on fire, it's over. All your data, it's over. It's gone. And it's also expensive. If every single time you have a new application, you need to go to your vendor and order a new server, that's a giant pain. It's really expensive. It has a lot of logistical issues. When's the server going to show up? You know, if you want to install QuickBooks at your company and you're suddenly ordering a server, that's not realistic. So virtual machines, they came in and they were the next thing that kind of solved this issue. The good, they're secure. You have Windows for every single one of your apps, or Linux if you're smart. You run multiple operating systems side by side. All of the servers that are running virtual machines have the exact same operating system. VMware, Windows Hyper-V, something of the sort, one of these things that allows you to have virtual machines. It doesn't do anything other than host other computers. The problems? Well, you have really bad performance. If for every single app you release, you're running a new instance of Windows. I mean, when your laptop's closed and you don't have any programs, you still notice it's using 1 gigabyte of RAM, 2 gigabytes of RAM, but there's nothing open, there's nothing happening. So if every app you have suddenly is using 2 gigabytes of RAM just because it uses Windows, that's a giant pain. It's an issue, and as you scale up, you're going to see suddenly, you know, you're wasting maybe 128 gigs of RAM just because you're running 64 Windows virtual machines. There's no real point in having all of that. So how would we get the best of both worlds in terms of, you know, virtual machines versus bare metal servers? The answer, it's containers. The difference between virtual machines and containers is that a virtual machine has virtual hardware. So if I have a Windows machine, it has a fake disk reader, it has a fake hard drive, it has a fake network card, it has all of these different things that it's emulating. just that you can have Windows in a little box. Containers, they don't do that. They skip that whole layer. So you have Windows on a machine, or for example, in this instance, Windows Server 2012. You have the container engine, something like Docker. And then each of your containers has its own little set of files. So they can't talk, they can't see each other's files, they can't interact with each other, they're isolated, but yet they still are able to work as if they were a host application. So it's a lot more efficient and it's a lot faster. So why containers? On the graph over here, I don't know if you're able to see, you have CPU benchmarks. So something like Computer Pi, this really shows awfully on the projector. But KVM right here is a virtual machine. All of these others are competitors in containerizations. There's different runtimes, kind of like how there's different versions of Windows. People make their own opinionated version of something that runs containers. And to be honest, they all perform pretty much the same. So native, that's going to be bare metal. Best performance, no matter what, always is going to be bare metal. It's about making that change as minimal as possible. So you can see here, a virtual machine to compute Pi, significantly slower than all of the container options. The container options are actually really close to the just bare metal deployment because they share the bare metal host. Memory benchmark, about the same, just really pretty negligible. Writing into disk, virtual machines are very slow writing to disk. Bare metal containers, very quick in comparison. Same goes for network benchmarks. It's the best way and the fastest way to run an application securely without needing to worry about virtual machines. It's faster. There's less overhead. You don't need to run Windows for every single app. It's isolated. They can't talk to each other. They can't break into each other. If you hack into a container, you're pretty screwed. You can't do anything. It's platform independent. If I make a container, I can hand it to someone here with a Mac and you can run it. I can hand the exact same container to somebody with a Windows computer. They can run it. If you're edgy and you run Linux like me, you can run it on your computer just fine. And it's also immutable. As soon as I make a container with my app and I put it in it, I say version 1. It does not change. No matter who downloads it where, I can't make a new version 1. Why? Because that would get confusing. How can you have two different version 1s? You have a version 1.1 or a version 1.2. It's set in stone. And no matter what, you can increase the version, but you can't remake the same container. At least you're not supposed to. So you put your apps in containers. Here's an example of how to put a Python app in a container. Really easy. You say from Python. Python has their own official containers. You copy all of the files for your Python app into the container. You install the requirements, because everybody here, I'm guessing at some point has tried to share a Python app with somebody that has requirements. And you're like, well, yeah, you have to run pip install. They're like, what does this module thing mean? I have to install Python on my computer. How do I do that? Python 2, Python 3, what? It's confusing. This way, you have a single app. You say it's Python 3.7. Whoever's downloading the container, they don't need to know any of this stuff. You wrote this, and it takes the files, copies them into the container. It installs the requirements inside of the container. And as soon as they run it, it's going to run what the CMD says. Python app py. Anybody can have that. Your app will run anywhere. That has Docker, that being said. Java, it's a little more complicated. There's Maven dependencies, as you probably worked with at some point. There's Gradle dependencies. Same idea. Copy all the files into the container. It's in a little package. And run Java jar, app jar. Easy. It'll run on Mac. It'll run on Windows. It'll run on Linux, and maybe a Razer toaster in 2023. Who knows? So to kind of summarize, containers for your application, they can run on any platform. They have all of the files needed to run the app. It's the best way to package any container. Applications that have a UI, it's not as useful. That's why you don't see it in Windows. You don't download a container. It's more for things like if you write a web app, if you're writing some kind of processing application or something of the sort. Why are they better? Faster, smaller disk usage, and they can't be changed. If I download the same container 50 years later with the same tag, version 1, I mean, it's going to be on ancient hardware probably, but it's still going to work. And all of the dependencies are already inside of there. I don't need to worry about NPM still being online, right? All the modules, all of those individual things are there, no matter what. How can you start with containers? Really easy. You need an app to containerize, obviously. You download a runtime. Docker is the best one. They support Windows, Mac, Linux, everything, and it's super easy. They're some of the founders of containers, even though people decided that they hated Docker. You create a Docker file. This is an example for Node.js. If anybody's worked with Node.js, really easy. You set the work directory, you copy the package JSON, install the dependencies, and then copy the assets. You publish your container to a registry. If you want to share your container with other people, you just take it almost like you take a zip file. You upload it somewhere, and then other people can download it, use that exact container. It'll run anywhere. It is the best way by far. All right. Let's talk about Kubernetes and what Kubernetes does. It's a little complicated, so bear with me. What does Kubernetes do other than have a fun name? It orchestrates containers. We were just talking about that. So any app that you can put in a container, Kubernetes can orchestrate. It manages state and it makes your infrastructure resilient. What do all these things mean? I'll get into it. Kubernetes was also founded by Google. Google originally created Kubernetes because they saw an unprecedented amount of users. They have so many requests. They have so many searches coming in. They had no idea how they were going to scale all of these servers. You know, they have probably thousands of servers. I'd argue maybe even 50,000 servers at this point. And they needed to manage all of them. So one of their employees invented Kubernetes. So let's get into what it is. Here's an example Kubernetes cluster. You have a control plane. You have the nodes. Each of these nodes is like a server. Think of it as an actual physical computer somewhere. It could be a virtual machine. That's confusing. They're physical servers for this example. So inside of here, let's say we have Pizza Shack, our new company. Pizza Shack has individual apps that they need to run. They have an employee portal app for people to put their timesheets in. They have a database to store all of the information. They have a pizza tracker. They have a static homepage, and they have an ordering web app. That's a lot of stuff to manage. And that's a pain to try and put into a bunch of virtual machines. So what do? We create a recipe, or also known as the state. So we tell the control plane, we say, control plane, hey, I want a static homepage. I want one ordering app to always be running. I want one database to always be running. I want one pizza tracker and one employee portal app. That's what I want you to do. Control plane, it has created each of those containers on all the nodes. So these three nodes are part of the cluster. The control plane, part of the cluster. They all work together to make this happen. And we'll break down the pieces of it. So what does Kubernetes offer in comparison to, you going, buying a server, putting Ubuntu on it, putting Windows Server on it? It's scalable. It's highly available, and it offers disaster recovery. We'll get into each of them. So scalability. What it does is what you're able to do is you're able to set desired values for your resource consumption. So let's say your app, as soon as it starts to see 80% CPU usage, starts to get really slow. It starts to be unpredictable. You don't know what it's going to do when it hits 90, and God help you if it hits 100%, right? That's really bad, especially for a company like Pizza Shack Inc. over here. So let's say your homepage target is 75% CPU usage. That's when it starts to get slow. You tell that to Kubernetes. You tell that to the control plane. You say 75% usage is what I want these apps to have, and if not, fix it. You have an ordering web app, you want to see 50% CPU usage. Any slow ordering app sucks for a company. They don't want to lose money. If people have a bad ordering experience, they might go to, someone else, Domino's. That would really suck for Pizza Shack. So as people start to use the actual container and they start to send requests, everybody's hungry, it's dinner time. The homepage app starts to see a ton of requests. It starts to heat up, right? So you see 80% CPU usage. Well, the control plane notices that. It knows homepage is supposed to be 75% CPU usage. So it will spawn another container on another node. Suddenly they've both balanced out. The requests for the hungry people are going to both of the homepage apps. It's scaled up. And as soon as it hits a lower point, you're able to also have it scale back down. So scalability, that's what it does. It's amazing. You can scale nodes. There's way more you can do with it, but that's a brief intro into what it does. High availability. So we have our recipe. We want 2 homepage containers and we want 2 ordering web apps on our cluster. Great. Why is 2 important? Well, because what happens if suddenly I decide I want to take this node out and I want to do maintenance. I want to update the operating system on it. What the control plane does is before it actually shuts that node down, it's going to spawn 2 new containers on other nodes, because the rule is there's always 2 homepages available. There's always 2 ordering web apps available. So it will make that happen. And I will have to wait until it's done spawning containers on other nodes. And then I will be able to take it into maintenance, maybe switch it out for a new physical server, change disks, whatever I have to do as the developer. The control plane, that's another thing. It's been this magical box to this point. I'll explain what it is a little bit. The control plane is just other servers. They're specialized though. And what they do is they run the Kubernetes internals. So you have things such as the internal database that it uses. We'll get into that later. And you have internal pods that do different tasks. The important thing to know is that as soon as you add something and you tell it, hey, 2 homepages, 2 ordering web apps, it's replicated. Every single server you add to your control plane will have an exact copy of that. So if one of them lights on fire, it doesn't matter necessarily. So high availability makes sense. We have nodes, we have a state that we need, and no matter what, it's going to make sure that state is always the case. Disaster recovery. This is a fun one. because I've had experience with it. So what happens if our beautiful cluster lights on fire? Well, firstly, your Monday really sucks. It was actually Wednesday for me. It was terrible. This was our Kubernetes cluster in Strasbourg. This entire data center burnt down. They shut it down, disks gone, right off. It was brutal. We had a cluster in this exact data center. I think it had about 40 nodes at the time, which was really not fun. I did not have a fun day. So it's very easy to perform disaster recovery with Kubernetes. You have this state. You know what's supposed to be happening. All you have to do is back your state up somewhere. And then as soon as you realize your Kubernetes cluster is lit on fire, you're worried, you think your day is completely ruined, you have a copy. You know what's supposed to be happening in the cluster. So all you do is you send the state to your new cluster that's in a different data center that hopefully is not on fire. And then suddenly everything is exactly as it is before. Back your state up. You can put it on GitHub. You can back up the actual database that's in Kubernetes, or you can use other orchestration tools. There's loads of them. You just save what's supposed to be in the cluster. If you make a new cluster, you can just copy paste. Super easy. Everything will happen automatically. So that's disaster recovery. How does it work? Well, Kubernetes at its core is just a database. That's all it is. Those control plane nodes that we were talking about, that's the core of Kubernetes. So here we have control plane. So as an example, let's say I want to deploy a Hello World pod onto a server. First, I create the Hello World pod as the developer. I say to the control plane, we're supposed to have one Hello World pod. I want that to run somewhere. The control plane does its magic. It decides where it's going to go, which node has room, where it's able to deploy it. Secondly, it actually schedules it. So the pod is put on to an individual node. And by pod, I mean container. A pod is just a container. It's the Kubernetes word. They have fun words for everything. So what does it actually do? What is this magical, mystical control plane that I've been talking about? It's really simple, and it's a really simple concept. It can get complicated, but the core is the most important part. It observes what's happening. And then, based on that, it checks what is supposed to be happening. Something like, I have one container, but this says I'm supposed to have two. Really simple. It observes, it says the difference is one container, it spawns a container. It does the same loop again, it's happy, there's two containers now, it's set. So it observes, it checks the difference, and it acts. It'll make changes to the actual cluster. So it'll store desired state, what you want. The current state doesn't match the desired state, it takes action. You as a developer, you can write code to choose what action's taken. If suddenly you know that it's not a big deal if one of your server's lights on fire, but only two, you can choose to do that. You can, as a developer, are able to write what happens in this loop, and you can write your own custom logic. But it comes built in with lovely logic because it's really hard to get into. So firstly, in a scenario of this, the control plane notices that node A is unavailable. It's on fire. Number two, the state says there should be a pod, but there isn't a pod. Three, the control plane schedules the pod on a different node to be able to be in the desired state. And that same loop happens, and it's fine. And it'll keep going, and nothing changes. But if node C were to light on fire, it would move it to node B. So what is the control plane? What actually is it? It's just nodes. I mentioned that earlier. It's just the same thing as these with a special label that says this is supposed to run critical infrastructure, not your pizza app. So in a simple sense, as a developer, you put something into etcd. That's the database that runs all of Kubernetes. It's strong, it's extremely resilient, and no matter what, if one of those database pods has something, unlike MySQL, MongoDB, something like that, where there's like a parent and it can be sort of, the data is written sort of everywhere, etcd is solid. No matter what, if you write something to it and it says, yes, this data is here, it is everywhere. You are guaranteed it. It was built specifically for this purpose, and it's built specifically for scaling infrastructure. So the developer runs a pod. They run a command like kubectl run, and then the container that we created earlier. It is stored in etcd. It's written to disk. That container is there. What happens next? Well, is after it's been replicated, the scheduler sees there's a pod, these pods here. They're watching for new pods to be created. That's their job. They're schedulers. They see there's a pod, but it's not actually ran somewhere. So it creates it on node C. And then suddenly the state was that there wasn't a pod, but there was a pod there, but it wasn't actually scheduled. It reconciled, it noticed there was a difference. It created it on node C. Happily ever after. So what is cluster state? I keep saying state, we store this in this. Really easy. Our two homepage containers, that's a config for it. It's just YAML. That's all state is. So if I want to run an app and I want it to be on the cluster, I just write a YAML and I run a command with the YAML in it, and it says, okay, cool, and it stores it. Now, the cool thing about this is your YAMLs can be in Bitbucket, GitHub, GitLab, anything. And that way, as soon as the data center burns down like ours, you're set. You're able to just take that repo and point it to another cluster, and all of your stuff comes back exactly how it should be. So in everything in Kubernetes, these are deployments specifically, you're able to configure it that way. So let's say you have secrets for your app. You have an API token to be able to send emails or SendGrid or something of the sort. They can be just like this, but instead of deployment, it's a config. Easy peasy. So the use case for gaming. I said I worked in gaming. I love gaming. It's my favorite thing, and it is the coolest thing to work with on Kubernetes because nobody does it. And these are probably industry secrets that I shouldn't be sharing. If my boss is watching, please don't fire me. But what do all three of these things have in common? Does anybody notice what the common thing between these games is? I'll give you a hint. It is the actual Q button. It's the find a server button. Every game has it. If you want to have a multiplayer game, you need a server. That's the reality of it. So let's say you have a game and you have all of these containers, right? Because obviously we all have decided that containers are by far the best way to deploy apps. They're amazing. So you have containers and each of your games is on there. So this server has 4 games. You're a new indie game developer. Well, a bunch of angry kids who come in and decide they're going to play the game, suddenly you've blown up. Your server can't handle all of that and your entire user base crashes and cannot play the game. Why? Because there's too many people demanding your server. It's out of resources. It happens. So more players means we need more servers, but that brings its own issues. How do we decide which server a player is going to connect to? How do we know, where we're going to schedule the game? How do we know that a server can actually take a game at that given point? These are all problems that Kubernetes has solved. Apparently, I've written over top of this, but how do we store a state of where all of the servers are and how they're running? Well, you have 2 options. You can decide that you want to use Kubernetes, which is the by far correct way. You don't need to maintain it. It's free. You don't need to reinvent the wheel. And collective innovation in any instance is always better than you doing it yourself. It's very easy to think I can do it myself. It'll be awesome. But let's be real, the hundreds of people who have contributed to the Kubernetes project, including Google's millions of dollars they pulled into it, definitely says a lot for it is a stable platform for running anything. Excuses to not use Kubernetes, which I've heard a lot of. Custom apps are more customizing. Yeah, they are, but you have to implement everything yourself. And we're all only one person. The reality is everybody works better as a team. If you are going to write something yourself, that's great, but you're not going to have the same amount of power that a project with hundreds of people contributing to it every single day have. Kubernetes has too many features. Kubernetes has a ton of features. It doesn't mean you have to use them. And there's absolutely no difference in performance if you don't use them. Kubernetes uses so little resources just to actually exist that it's negligible to any point. And when Kubernetes starts to use resources, that means you have a lot of people using your app. So if you have issues with that, you're not monetizing correctly. It's more secure than, maybe using my own solution. That's absolutely not true. The US Department of Defense uses Kubernetes for processing data. I actually interviewed with the company recently, and they were talking, the guy who was the head of their Kubernetes team was talking about how they used Kubernetes to do graphics card processing between containers. Why'd they pick it? Because it was more secure than their original app, and they had issues maintaining it. You only use Windows Server. If you use Windows Server, I don't know why you're getting a computer science degree. Okay, managing the nodes. We have a very bad way of doing this. This is without Kubernetes. And this is actually something that our company did use and eventually switched it out. Why? Because it was technical debt. It was a big problem and it caused us a lot of issues. So let's say we write a manager app. Our manager app is going to supervise all the individual little servers, right? Each machine has an app on it. The avocado, we actually called the project Avocado. It was fantastic. Each app has an avocado on it. It manages the individual little servers that are happening. Maybe it uses containers, whatever it might use. Your manager app basically will get a request from a player who wants a game, right? That makes sense. When you want a game, you need to find a server first. It'll find a server talking to each of the nodes. Maybe this one's full, so it can't take a server, but this one's a good selection for whatever logic you've written. The app will give the player a server, and the player would connect. Simple concept, right? And then that way you're set. Because, if there's some issue, then the manager app will know. What's the problem? Well, again, you think it's fine. This server's on fire, that server's on fire. We won't connect players to that. The manager app knows the server's on fire. The problem is that the manager app has to run on the server too. And now you're in a bit of a conundrum, because what happens if this light's on fire? The answer is that everything is on fire. Everything does not work. And this also happened to us. We lost 50,000 players simultaneously because of this exact scenario. A technician unplugged the wrong Ethernet cable. So back to the upcut. We're primed with our Kubernetes knowledge, right? And we can talk about the right way. So how should it work? Very simple. You have games. They run on the nodes. We know containers can run on Kubernetes nodes. That's easy peasy stuff. But a user would request a game from the game manager, right? And we have two of them, high availability. If this server dies out, then that server also has a game manager. We're set. So now this game manager is inside of the cluster. It knows I need to create a new game for this player. All of these games are busy. They're all running. I need to make a new one. Game manager talks to the Kubernetes API. The Kubernetes API, as a developer, you can do anything. If you have some random app that has to run because the user clicks a button, you can do that. You just tell it, hey, you add into the state, hey, I want a pod, I want it to be running, and I want you to do it. And it will say, okay, no problem. And it makes it happen. So the game manager creates a pod in Kubernetes. It waits for it to get scheduled somewhere. The game pod is scheduled on any node that's available. So in this case, node B is definitely not an option. It's full, right? So it'll pick A, B, or C. In this case, it picks C, and you can have you see the new game server there. Now, the game pod's IP is sent back to the player, and the player can connect to the game server. Easy peasy. So what are the key takeaways from this that are important? Well, firstly, containers are awesome, not just with Kubernetes, but through anything. If you're developing code and you're sharing it with other developers, maybe you're a backend developer and someone's a front-end developer, it's the easiest way to share it. Nobody likes installing node modules. It's the worst thing in the world. If you put it inside of a container, it's easy. Anybody can run it. You don't need to install it. You just download it and it runs. Kubernetes is an asset for any production application. It's scalable, it's fault tolerant, and it's resilient. No matter what you deploy, if you put it on Kubernetes, it's going to stay there and it's going to stay strong as long as you maintain your cluster. Kubernetes solves state management for infrastructure. Has anybody gone into an existing company before and written code before or changed something? Okay, you're all in for a really rough time. It is very difficult to understand what's going on, especially with infrastructure. You'll have somebody say, we have this web server, but then we had to make a new web server, but there's the third web server just in case these two die. And it gets really complicated. There's all these different places. You have documentation in Notion about what's happening. You have maybe some markdown files in GitHub talking about where all of this infrastructure is. Kubernetes, it's all in one place. All of it is the state. It's all YAML files. If you want to know what's running, you look at the YAML files and it says, this is what's happening inside of the cluster. This is where the containers are. These are the rules. And also, well, it's daunting. It's your best friend when you really need it. If you ever are trying to scale something, try writing your own app. Give it a shot if you have the free time. It is a nightmare. You will not have a good time. And that's it. Thank you. So when I originally signed up for this, I found out I was doing this talk on Monday. There was something that said there would be an interactive portion. I don't know. I didn't have time for that. So in terms of actually working with Kubernetes, I'm not opposed to ever doing a workshop or something like that, if that's something people are interested in. You guys can maybe give me a show of hands if you'd be interested in a workshop where you actually get to deploy stuff. Cool. Now, how many of you are available during the reading week? Not a bad number. Okay. I'll see if I'm able to run something during the reading week where everybody's able to just have an interactive thing. We'll work with an actual cluster. We'll maybe write an app in your free time or whatever. You can bring an app in. I'll show you how to turn it into a container, and I'll show you how to put it on Kubernetes. But in terms of time, I didn't have enough for this. I barely had enough time to make the slides. But yeah, is there any questions? Does anybody want to know anything? Yeah.
So the control panel controls your physical service.
The control plane is, let me actually go back. I'll be better at explaining this if I have the actual thing. So the control plane is just Kubernetes, but it's internal. So go back. Here we go. Yeah, so the control plane. So these are the nodes, right? These are physical servers. These also, each of these blue boxes is also a physical server. So the difference between a control plane node and a worker node is that the control plane node doesn't have user scheduled pods. It has Kubernetes pods. So the scheduler, it's in charge of putting pods on these actual nodes. There's other ones like the disk manager pod. and it will look into the actual nodes to see, are your disks configured the right way? Is all of this data consistent? So each of these is a physical server, but the only difference between these things and these things is these ones run the user workload, these ones run the system workloads. It's kind of like, I don't know, in Windows where you have System 32, things like that. You don't really touch your programs in there, but there are programs.
So the nodes below are the ones you own, basically.
Exactly. You own these too, right? You pay for these nodes, but their main job is just managing stuff. So if you wrote custom logic and in Kubernetes, you can write anything. You can make your own kind of something. So let's say you decide to write an app. Your app requires MySQL. Your app requires 2 web servers, and it's some kind of accounting app. And you want people to be able to deploy it easily on Kubernetes. You can write a pod that goes in here, and it listens for that, and it knows to create all of those things on the nodes. So system internal things for Kubernetes belong on the master nodes. And then those master nodes are basically in charge of the entire cluster. You could, if you wanted, you could put your pizza tracker on here. That is an option, but it's a terrible idea. And in terms of the Kubernetes ecosystem, they've always suggested you separate the two. And it's a lot easier to understand when you kind of separate the two as well. Anyone else?
Yes. So like what if the national like catch fire like
Yes, good question. So if one of the master nodes lights on fire, let's say master node 3 suddenly is in that data center that burnt down with the rest of our data, RIP data. So if this one burns down, these 2 containers have an exact copy. So when you run a pod, it's mirrored between all of these. So if this node goes out, these 2 can still talk. It's not a problem. If you lose all of your master nodes to a point where you only have 1 left, you will have to restart your entire cluster, and it sucks. So it's really advisable to always have 3 because the odds of 2 of them dying is very low. You put them in separate server racks. So if the technician trips over the cable, you have extra ones. And there's no limit. You don't need to have 3 master nodes. You can have unlimited. The only downside is that you have to pay for them, obviously, and they need to be something. But yeah, some providers like Google Cloud will host these master nodes for you. So you don't actually even pay for them. You just pay $20 a month. They host master nodes for you. You don't need to worry about it, which is pretty fantastic in a lot of cases. But in terms of Kubernetes, I'm not trying to sell a cloud or anything here. Master nodes are a thing. Google's just dealing with them for you. Anyone else? Yeah.
In terms of the code, you said that, so the code that you showed for putting a program into containers, is just like 3 or 4 times, or is there more to it?
So it depends. So inside of a container, let me go back all the way to our slide of Docker containers. Here we go. So yeah. So for Python's really easy. So think of it, how many of you have used Linux before in some case, or ever just ran commands in a command prompt? Right, okay. That's pretty good. So in Linux, you run commands, obviously. So think of this container script is running on a Linux server. So in this case, Python, when you have dependencies, you have your pip dependencies, right? Those are all the things you've imported in. Someone else has written that. So if I were to run this exact app that's here theoretically on some random server that I bought on Google Cloud, on AWS, first command I'm going to run is I'm going to copy all the files from my local machine to the server. Second thing I'm going to do is on that server, I would install the dependencies. And the third thing is I would run the command, right? This is creating almost a virtual machine in a sense. So these are instructions. These say right now on my developer machine, run these things. So copy all the files, pip install all the dependencies, and then it takes all that and it zips it. Now, as soon as somebody else takes this container and they run it, it doesn't do any of this. That doesn't matter. It's already been done on your developer machine. This last line is exactly what it does. So it runs Python app py, which starts it. It already has all the dependencies there, and you don't need to have the CPU resources to download all your pip dependencies or anything like that. Does that kind of make sense? Does that answer your question?
Yes, it does. So for Python, basically you would add those 4 lines.
Yes.
Okay.
Yeah, exactly. And suddenly, if you had some graphics in Python or some weird library that you needed, you just add another line. Run apt install if you use Ubuntu Linux, or DNF install if you're using Fedora Linux, whatever it might be. But those are the commands that it's going to run when it builds the container. It's like running a formula for a virtual machine, right? Or like making pre-baked pancake ingredients that people can go and shove it in their oven. Easy.
So basically, Kubernetes is just a simplified version of Linux. Can you say that? Like it's a simplified operating system.
Good question. So Kubernetes itself is not an operating system. You can run Kubernetes on Ubuntu server. You can run Kubernetes on Linux. A lot of people will use core operating systems, Fedora Core OS. So the idea of Kubernetes is that it's not necessarily an operating system that you install. You install whatever operating system you want. You install it as a package in that operating system.
Okay.
So it'd be like you install Ubuntu. If you want to add a new member to your Kubernetes cluster, and you buy this big server, you install Ubuntu server on it. You then install Kubernetes on it, and then from the existing Kubernetes cluster, if you have one, you join it in.
Every node has to have an operating system.
Yes, every node has to have an operating system.
So how's that different than any like,
Virtual machines.
yeah,
So the difference between virtual machines is that if you have, I went too far, sorry. If you have, oh no, I didn't. I went. If you have virtual machines, every app needs its own VM, right? So the issue is for every app you deploy, in our pizza example, the pizza tracker is going to have its own OS.
Yeah.
Right. The static web app is going to have its own OS.
Okay.
And so just in those two, we have 4 GB of RAM that are just going to the system. Versus if you use Kubernetes, that 2 GB is shared across all of them. So they don't each have to have, that overhead, and they're still separated.
We have a question on Zoom.
Yes.
So the question is, if I will be using Kubernetes on cloud, which platform, AWS, Azure, and GCP would you recommend?
I mean, going back to the Google Cloud Google made Kubernetes. Google has the by far best Kubernetes API, in my opinion, in terms of working with it, adding nodes, doing anything. Google Cloud is by far the best, and they're probably one of the cheapest too, I'd say. Anything else? Cool. Okay. Hopefully I didn't bore you guys too much. I will talk with Jen to see if we're able to schedule in at some point some kind of workshop. I'll write something interactive so all of us can deploy an app. If you're interested in that, I mean, obviously all you are, but I'll send a link inside of Slack or something like that to try and arrange a day. And yeah, that's pretty much it. Well, they're free to leave. Whose laptop did it? Is it yours? Thank you. I appreciate it. You actually